Welcome to MatSci Simple, where complex engineering and science is broken down into simple, clear, visual explanations. Whether you are a student, a GATE aspirant, or simply curious about the world around you, this channel is made for you. Hit subscribe so you never miss one. Steel is 12 times stronger than pure iron. Same base element. Less than 2% carbon added. Completely different material. How? That is exactly what this episode is going to answer. Today we go deep into metals, the most widely used family of engineering materials on Earth. By the end of this episode, you will understand exactly what happens inside a metal at the atomic level and why that matters. Most people think of metals as shiny, hard objects, but that is the appearance, not the definition. A metal is defined by one thing: free electrons. Inside every metal, the outermost electrons of each atom are not held tightly to any one atom. They break free and float through the entire material. Scientists call this the sea of electrons model. Look at the diagram on screen. The large gray spheres are the positively charged metal ion cores, sitting in fixed positions. The small teal spheres are the free electrons, drifting freely between them. And this one structural feature, free electrons, explains all four key properties of metals. Electrical conductivity. Free electrons flow and carry current. That is why copper wire powers your home. Thermal conductivity. The same electrons carry heat energy rapidly. That is why a metal spoon in hot tea becomes warm almost instantly. Ductility. The electron cloud allows atomic layers to slide over each other without the bonds breaking. That is why you can bend a copper wire without it snapping. And metallic luster. Free electrons absorb and re-emit light. That is the source of the characteristic metallic shine. One structural feature. Four key properties. This is the power of understanding materials at the atomic level. Now here is something that surprises most students. Inside every metal, atoms are not randomly scattered. They sit in a precise, three-dimensional repeating pattern called a crystal lattice. And this pattern, this structure, determines how the metal behaves under stress. There are three main crystal structures in engineering metals. The first is BCC, body-centered cubic. Picture a cube with one atom at each of the 8 corners and one atom right at the center. Iron at room temperature has this structure. 2 atoms per unit cell, coordination number 8. BCC metals are strong but relatively less ductile. The second is FCC, face-centered cubic. Same cube, but now there is also one atom at the center of each face. Aluminum, copper, gold, and nickel are all FCC. 4 atoms per unit cell, coordination number 12. FCC metals are highly ductile. They have 12 slip systems, meaning atomic planes can slide easily past each other. The third is HCP, hexagonal close packed. 2 hexagonal layers of atoms with 3 atoms nestled in between. Titanium and magnesium have this structure. Also coordination number 12, but with fewer independent slip systems than FCC, so HCP metals are less ductile. The key insight: FCC metals are the most ductile because they have the most slip systems. The crystal structure controls how atoms can move, and that controls everything. Now let us look at the most famous comparison in metals engineering: iron versus steel. On the left you can see pure iron. It has 0 carbon. Its crystal structure is BCC at room temperature. Its tensile strength is around 210 megapascals. It scratches easily, rusts rapidly, and has very limited engineering use because it is simply too soft. Now look at the right side, steel. It is iron with a small amount of carbon added, typically between 0.2 and 2.1%. In the diagram, you can see the yellow carbon atoms sitting in the gaps between iron atoms. These interstitial positions are the key. The carbon atoms distort the BCC lattice slightly, making it much harder for atomic planes to slip past each other. The result is dramatic. Tensile strength jumps to anywhere between 400 and 2,500 megapascals, up to 12 times stronger than pure iron. The ductility of steel is also adjustable through heat treatment, which we will cover in the next episode. Same base element, less than 2% addition. The difference between a material that barely has any use and one that builds bridges, ships, and skyscrapers. Here is something that surprises almost everyone. When you look at a piece of steel under a microscope, it does not look like one perfect crystal. It looks like a mosaic, millions of tiny crystals packed together. Each one is called a grain. You can see this in the diagram. Each colored region is one individual grain with its own crystal orientation. The lines between them are grain boundaries. When stress is applied to a metal, atomic planes try to slip. But grain boundaries act like walls. When a dislocation, a moving defect in the crystal, reaches a grain boundary, it cannot easily cross into the next grain because the orientation is different. The movement is stopped. Smaller grains mean more grain boundaries. More grain boundaries mean more barriers to dislocation movement. More barriers means a stronger, harder metal. This relationship has a name, the Hall-Petch relationship. It states that yield strength increases as grain size decreases. In practice, engineers control grain size by controlling how quickly the metal cools during processing. Faster cooling gives smaller grains and a stronger metal. So far, we have talked about pure metals, but most engineering metals are not pure, they are alloys. An alloy is a metal mixed with one or more elements to create a material with better properties than either starting element alone. There are two types of alloys. In a substitutional alloy, some host atoms are replaced by solute atoms of a similar size. Brass is a good example, copper atoms replaced by zinc atoms. In an interstitial alloy, smaller atoms fit into the gaps between the host atoms. Steel is the most important example. Small carbon atoms sit in the gaps between iron atoms, distorting the lattice and multiplying the strength. Look at the 6 alloys on the right. Steel, iron plus carbon, the most produced engineering material on Earth. Stainless steel, iron plus chromium and nickel. The chromium forms an invisible protective oxide layer on the surface, making it corrosion resistant. That is why your kitchen utensils do not rust. Duralumin, aluminum plus copper and magnesium. 2.8 grams per cubic centimeter, yet comparable strength to mild steel, used throughout the aerospace industry. Brass, bronze, nichrome, each one engineered for a specific purpose. Every alloy is an engineering decision. What properties do you need and what do you add to achieve them? Let us now connect everything we have learned to real engineering structures. The Eiffel Tower, completed in 1889, used wrought iron, not steel. Ductility was the critical factor. The structure needed to be assembled from 18,000 prefabricated parts, bolted together on site. Brittle cast iron would have cracked under the fabrication stresses. Wrought iron's ductility made it possible. The tower also expands by 15 centimeters in summer due to thermal expansion. This was designed in from the beginning. The Golden Gate Bridge used 83,000 tons of high-tensile carbon steel. The main suspension cables contain 27,572 individual wires, each with a tensile strength of 1,600 megapascals. That extreme strength was necessary to span 1.3 kilometers of water with minimal sag. Jet engine turbine blades face perhaps the most extreme conditions of any engineering component. They operate at 1400 degrees Celsius, above the melting point of ordinary steel. The solution is nickel superalloys, manufactured as single crystals with no grain boundaries at all. Grain boundaries are the weak points at high temperature, so engineers eliminated them entirely. Railway tracks use high carbon perlytic steel with a hardness between 260 and 320 on the Brinell scale. For railway tracks, hardness and wear resistance matter far more than ductility. Every application selects and engineers the right metal for the right job. That is applied materials science. Let us recap the 5 key things from today. Metals are defined by free electrons. That one feature gives them conductivity, ductility, and luster. Atoms arrange into crystal lattices, BCC, FCC, or HCP, and the structure controls how easily atoms can slip, which controls ductility and strength. Steel is iron with carbon in the interstitial gaps. That small addition blocks slip planes and multiplies strength by up to 12 times. Grain boundaries stop dislocation movement. Smaller grains mean more boundaries, which means a stronger metal. This is the Hall-Petch relationship. And alloys combine elements to create materials better than either starting element alone. Steel, stainless steel, duralumin, all engineered for specific applications. In the next episode, Metals Part 2, we go even deeper. We will look at the stress-strain curve in detail and heat treatment processes including annealing, normalizing, quenching, and tempering. We will see how the exact same steel can be made either soft and workable or extremely hard and brittle just by changing the heat treatment. If this video helped you understand metals better, please like it and subscribe. Drop a comment below which real-world application surprised you the most. I read every single one. See you in the next one.